Hello, hello. All right, so we're gonna start chapter 2 today. We are going to make this magical jump from algebra, okay, to calculus. And I'm just going to do some notes here before we jump onto the actual printed notes. So if you're following along, obviously you're watching. You can just watch this development here, and then when I get back to the real notes, you can start filling in. Okay, so things you guys should definitely be comfortable with. We've got algebra, right? And back in algebra, we had some function, right? And maybe it looks like this, okay? And you have this point C, and so that right there would be f of C. And then over here, we've got some different distance. Maybe we're up here at x, and then right there, we would be at f of x. And so in algebra, you could estimate the rate of change, right? This is not a straight line. This is a function. But you guys should be able to find the slope through 2 points. And we know we need 2 points to find the slope. Okay, and so if you wanted to find the slope of that line, which is a fancy word for rate of change, right? It's real simple. It would do y2 minus y1, or f of x minus f of c, over x2 minus x1, x minus c. Okay, and so hopefully that doesn't confuse you, right? You have a function. It's not a straight line, but if we're given any 2 points, we could find the slope. And that's algebra. Okay, well, what happens is we're trying to make this transition to calculus, and this is like the biggest concept so far, right? How do I go to calculus? Well, what calculus does is it says, all right, let's take a graph, and let's take a similar function there, right? And then it goes right here to C, and it says, hey, I want not the average rate of change, I want the instantaneous rate of change. Okay, and then right there at C. So I want to know, hey, what's the rate of change at C? We have a huge problem, you guys, right? Like we had 2 points here. This was super easy because I know how to find the slope through 2 points. Okay, so how do I find the instantaneous at 1 point? Well, let's play around with this. Let's say that I move x closer, right? So up here, see how x is really far away? Let's take this random point here, and let's come up here, and let's do the same thing, right? We would get this line that goes through those 2 points, and we would do the same thing. We'd say, look, it's f of x minus f of c over x minus c. But in theory, you guys, this isn't instantaneous because I still have these 2 points. But if I put this in front, look what happens. I'm slamming x towards c. So in theory, this point is so ridiculously close to this point, it's basically just one big point, and you're coming up with the instantaneous rate of change. So the instantaneous part, you add in this limit process where you slam these 2 points close together, and they're so close together, right? As it comes back here, you're right there, and you can find the slope of that line, which ends up being tangent, and it is the instantaneous rate of change. Okay? So on these notes, you can see here that you've got these 3 graphs, and they do kind of a good job, right? They start you with these 2 points, and you've got this secant line, which is from algebra 1. But as you move this x towards c here, right, this secant line starts sliding down, right? If it comes here, now all of a sudden it looks like that. And then if it comes here, it looks like this, and so forth, until you get what you're going for, your tangent line, which is the instantaneous rate of change. And so the only difference here, right, you can see that x is approaching c. That becomes calculus. Okay, so it's just the slope formula with the limit process in front. And what that is, that entire thing right there, you guys, is actually the definition of a derivative at a point. Okay, and you have to be able to talk about this, and we're just learning it now, but we'll deal with this a lot. The derivative is the instantaneous rate of change, right? So stocks go up and down throughout a day. Right there, what's happening? Well, we have a tangent line. The rate of change at that instant is positive, call it 1, right? So you're coming up with that slope that's right there. Okay, we're going to write equations of tangent lines, right? And the easiest way to do this is point slope form. Maybe you remember this, point slope form. What do you need for point slope form? You need a point, right? X, Y, and you need a slope. Okay, and so the derivative gives us the slope, and then we'll have a point that we can use. Okay, so let's get in here and do an example. It says finding equations of tangent line and the normal line. Normal line, remember, is just a perpendicular line. So let's find the slope of a tangent line given this function. Okay, you guys know a lot about this function. This is y equals x squared. It's a parabola. It's a polynomial. It's continuous, no holes, no weird stuff. And we want to know what's going on at -2. Okay, so find the slope. That is telling you to use the derivative. Okay, underline, definition based. The derivative, f prime at this c value, -2, right? All I'm doing is I'm using this formula right here, okay, is equal to the limit as x approaches c, or as x approaches -2, of f of x, so we write f of x, minus f of c, right there, so that's f of -2, all over x minus c, so x minus a -2. Okay, and let's continue and fill things in that we know. So it's the limit as x approaches -2. Well, what is f of x? It tells us right there it's x squared. So I have x squared minus f of -2. Well, if I plug in -2 to the function, I get -2 quantity squared, which is +4. So I've got x squared minus 4. All over the bottom becomes x plus 2. And we're back to chapter 1. First rule of limits is direct substitution. Direct substitution yields 4 minus 4 over -2 plus 2, which is 0 over 0. You're supposed to do stuff, right? So what does that mean? Well, if you pass the test, you should factor cancel. So let's retake the limit as x goes to -2 of x plus 2 times x minus 2 all over x plus 2. This is a removable point of discontinuity. At -2, the function is undefined because it's 0 in the denominator. But since you can cancel it, technically you're removing it, which makes it a whole at -2. Regardless, you factor cancel, you plug in -2, you get -2 minus 2, which is -4. Okay? All right, so we use this understanding of limits from chapter 1 to plug into this definition and evaluate. And so look what we found, you guys. We found the derivative at -2 is equal to -4, right? In your brain, what the heck does that mean? What does f prime of -2 equal -4 mean? It means that the instantaneous rate of change at x equals -2 is -4. Okay? And let's talk about that graphically, you guys, right? We're dealing with something that you guys know real well. Y equals x squared. I'm back here at -2. There is a tangent line right there, and we just found the slope of that guy. It's -4. Okay, so again, as you go back through and you rewatch this, this looks horrible, but this is a parabola, and you're finding a tangent line, right, using calculus. Because we only have one point, we use this limit process to get the slope of that tangent line. And so if you want an equation of a line, right, you have a point, -2, 4. You have a slope, f prime at -2 is equal to -4. And with that, you can write your tangent line right up here. Okay, point slope form. You guys might remember it as y minus y1 equals m times x minus x1. That's fine. But what's up with this? Well, just move this guy to the other side and it becomes positive. Okay, so in calc, always the way that we're going to write our lines, we're going to say y equals, okay, the y value. What's the y value? 4. Right? Minus the slope times x minus the x value there. Okay? Which is simply 4 minus 4 times x plus 2. And you guys can leave it like that. Okay? And so we have y equals that. That is our tangent line. Okay? So I'm going to abbreviate that as tangent line. That's great. What about the normal line? Super easy, right? A perpendicular slope to -4 is positive 1/4. And so your normal line would be y equals 4 plus 1/4 times x plus 2. All that's changed, right, is your slope value there because it's normal, which is perpendicular. Okay? All right. Let's see what they ask us next. So at the top of the next page, they say, all right, so use the result to find the equation of a tangent line when c is -2. Find the equation of a normal line. Man, we did all this, right? So we did it all in part A. So in part A, we found it. Did more than an ask. It just said find the slope. So for part A, your slope is done when you get right here. Okay, part B was find the equation of a tangent line, which we said was y equals 4 minus 4 times x plus 2. And then normal line, right, was the perpendicular. So we said that's y equals 4 plus 1/4, opposite reciprocal, times x plus 2. Okay, and now let's do it again. So we get to start all over. And we're going to do this whole process again. Here it should go a little bit faster. So you need to find f prime at c, which is f prime at 1. Well, what does that equal to? That is equal to f of x, which is x cubed, okay, minus f of c. So I'm using this. It's on the front. I'll just rewrite it here. And it's the limit as x approaches c. Okay. All right, so we've got our x cubed, which is f of x, minus f of c. Well, what's f of c? F of c is f of 1, or 1 cubed, which is just 1, all over x minus c, or x minus 1, because c is equal to 1. All right, from pre-calculus, this is factorable. This is the difference of two perfect cubes. This is x minus 1 times x squared. I don't know how you guys learned this. I just memorized minus, minus, plus, plus. Okay, you could always review that minus, minus, plus, plus, or maybe they do same, opposite, positive. This is the difference of two cubes, though, so you can review that. Over x minus 1, we're good to go. Okay, these guys will cancel. And remember here that we need our limit as x approaches 1. Okay, and so direct substitution, we factor canceled because we got a 0 over 0 here. You plug in 1, and you get 1 squared plus 1, or 3. Okay, so we have a slope. So we have that f prime at 1 is equal to 3. The slope of the tangent line at an x value of 1 is 3. Okay, graphically, you guys know x cubed looks like this. We're over here to value of 1. Right there, the slope is equal to 3. Okay, all right, so we've got our slope, we've got our point. You plug in 1 to 1 cubed and you get 1. And so our tangent line, right, I'll call it y sub t for tangent, is equal to the y value, which is 1, plus the slope, or plus 3 times x minus the x value. Okay, if you want the normal line, all you do is you take the opposite reciprocal, so that becomes 1 minus 1/3 times x minus 1, and you're good to go. Okay, all right, let's do one more. Hopefully this gets a little bit easier. Again, these are functions that you know. This is a parabola that's got some other stuff going on because you've got an x term in it. But at the end of the day, they want to find the rate of change at 2, okay, and then at any real number c. So rate of change is not calculus, okay? Rate of change is algebra. The rate of change is simply f of x minus f of c over x minus c, okay? So for a, if c is 2, right, f of x minus f of c over x minus c would simply be the function value, which is x squared minus 5x, minus f of c. Well, if c is 2, you're subtracting 2 squared minus 5 times 2, all over x minus c, or x minus 2. So let's simplify. This becomes x squared minus 5x. This becomes 4, but that's minus, so minus 4. This becomes a minus 10. Well, that's kind of silly. Let's not do it that way. Let's do 4 minus 10 here and get negative 6. So this just becomes plus 6 over x minus 2. Okay, and we can simplify that because we know that that factors into x minus 3 times x minus 2, because negative 3, negative 2, positive 6. They also add up to negative 5 over x minus 2, and those cancel. And we get an answer of x minus 3. Okay, and so if c is 2, the rate of change anywhere, right, at any x value is going to be that. At any real number c, what's that saying? Well, that's not giving us a numerical value, right? So for part B, f of x minus f of c over x minus c, okay, we don't know the numerical value for c, but we can still proceed. We can plug in for the function value here, which is x squared minus 5x, and then minus f of c. Well, what's f of c? F of 1 is 1 squared minus 5 times 1. F of 2 is 2 squared minus 5 times 2. F of c is c squared minus 5c. Okay, all over x minus c. So let's see if anything fancy happens here. This ends up getting x squared minus 5x minus c squared minus 5c all over x minus c. Okay, and we're there. I don't know. I must have got this out of some textbook. I'm trying to figure out why that's important for us. But I guess, for any real number c, that would be our rate of change. Okay. Maybe can we play around here and take an x out and get x times x minus 5 minus c times c minus 5 over x minus c? Okay. That would be really good if we could factor that by grouping, but we can't take out anything there, so I think we're good here. So we'll stop there. If for some reason I'm missing something, I'll go back and check the textbook and see if they wanted us to do anything different. I think we're good. Okay, so to summarize here, right, that was a lot. Basically, you guys in Algebra 1, given any 2 points, you should be able to find the slope, right, through those 2 points. What calculus does is it wants the instantaneous. And so what we do is we act like there's this second point, but we make them so ridiculously close together that it is exactly at 1 point, which is using calculus procedures of the limit. Okay, and what can we do with that? By doing that, you're actually finding what we're going to call the derivative in calculus, which is the slope, right, of a tangent line. Okay, it says here it's the instantaneous rate of change. That's true. It's the slope of tangent line at any x value. Okay, and so once we found the slope, we could write equations of lines. So just make sure you review. Point slope form is this, but if you add the y to the other side, you just get y equals y1 plus the slope times x minus x1. And in calculus, we're always going to be finding the derivative, which gives us the slope. We have this random point that we find the slope at, and so it's easy to come up with tangent lines and normal lines. Okay, all right, guys, take care.